So part B asks us to do a couple things. First off, it's going to ask us for a tank with a variable volume, constant cross-section, and perfectly stirred with time-varying inlet flow and concentration. We're going to derive some differential equations for the concentration and liquid level in the tank. So if we were to take a look at this tank, it's going to look something like this, where we have our tank, we have some liquid level, we have some flow in. Okay. At some concentration, it is perfectly stirred. We have a nice little stir over here. And we have a flow out, which, remember, is equal to the cross-section of the drainage hole times the square root of 2g times half the height to the half power. And so with this system, what we have to go ahead and do now is we're going to derive some differential equations that will derive the concentration and the liquid level at the tank at a certain time. So the first differential equation that we have to go ahead and account for is the fact that we have a changing volume over time. And this can be simply rewritten as just the Q in minus the Q out, just a difference in our flows. But this is too simple for us. We need to spice it up a little bit. So we know that the Q in, we're just going to keep that as a Q in, that is some initial flow rate. And the Q out is equal to, well, it's equal to this thing right here. So let's go ahead, let's use that. So A of the drainage hole times square root of 2g height to the 1/2. That's going to be our Q out. And we can rewrite our dV dt as well as the cross-sectional area times dH dt. And we can go ahead, we'll divide by the cross-sectional area on both sides. And so the first differential equation that we end up with is dH dt is equal to Qn minus area of the drainage hole times square root of 2g times h to the 1/2 power all over AC. So here is differential equation number 1. Now we're going to be a bit more technical with the second differential equation, and what I mean by that is when we look at our tank system here, we notice a couple things. First off, it's a perfectly stirred tank. So whatever the concentration at inside the tank is, that is going to be equal to the concentration inside the tank. So that's the first thing that we know. Now we know that between the inlet concentration and the concentration in the tank, there's going to be some difference. There's going to be a change in that concentration because we're increasing that volume over time. So our next differential equation is going to focus on the change of concentration and volume over time. And essentially what we have here, this is going to be equal to the Q in times C in minus the Q out times C out. So we can go ahead, we can start focusing on plugging some things in. Now, we know that when we talk about volume, we're essentially talking about the cross-sectional area times the height. However, the cross-sectional area is a constant and the height is not. So we're going to rewrite this as AC times dCH dt. And what that denotates is now we are looking at the cross-sectional area times the rate of change of the concentration with height. Now this is going to be equal to Q in, C in. These are flow rates that we can't, this is a flow rate that is initial. This is a concentration that is initial. So these are values that we should have. Minus. Now Q out. Well, actually, let's talk about the concentration first. We already said that the concentration coming out of the tank is going to be equal to the concentration inside the tank, so we're just going to label that C. And our Q out, as always, is the area of the drainage hole times the square root of 2g times h to the 1/2. Now, what we can end up doing is we'll divide over by the cross-sectional area, so dCH over dt equals Q in C in minus C times ADH square root of 2g h to 1/2 all over cross-sectional area. Now, when we look at this derivative here, we notice that there's a product rule going on, and the product rule is between this concentration and height. So essentially, what we're getting here is our concentration times dH dt plus our height times dC dt. And that's equal to, well, that's equal to all this. So just going to copy you and paste it right there. Gotta love technology. Now, we really want to isolate this term right here. And the way we're going to do that is we're going to bring this term over to the right side, and we'll divide everything by h, or multiply by 1 over h, since, you know, we don't want a big, really confusing fraction. So what we end up with is dc dt is equal to Control C, Control V, and we are going to now we're going to subtract the concentration times the rate of change of the height, and we're going to multiply this entire thing by 1 over h. And with that, we now have our second differential equation we're going to use to solve for part B. So now we're in Python for the second part of this part B, and I'm going to pull up the constants I have on my second monitor. So now it's telling us that we're going to start from an initial steady state where the flow into the tank is 0.1 meters cubed per second. So first off, we're going to define our G. We'll be using that in a bit, and that's in meters per second squared. So the first thing is initial steady state. So we're going to go Q in initial is going to be equal to 0.1 meters cubed per second. And I'm also going to go ahead and the initial concentration. So we're going to go C in initial is 1.0 moles per meter cubed. Ooh. Mole per meter cubed. Now the inlet flow rate increases by 10% at time equals 0. So we're going to go Q in equals Q in naught times 1.1. And the inlet concentration increases by 25% at t equals 0. So we're going to go Cn equals C in naught times 1.25. And these are still in the same units, so just going to hit the Control C, Control V a couple times, get that all nice and sorted. We have a cross-sectional area of 1 meter squared. Meter squared. A drainage hole area, so ADH, is 0.01 meters squared. And we can also calculate for the initial height using this equation. And that equation is going to be Qn naught, so that's at the steady state, squared, divided by the area of the drainage hole, A dH squared, times 2 times G. And those are all the givens for this problem. Now we can go ahead, import our differential equation functions, and use solve IVP to go ahead and simulate this tank. So we're going to go ahead, we're going to define this function dv dt, where we have inputs of time and volume. And first things first, we're going to unpack this into the height and concentration. So height, concentration equals V. So we can go ahead. We're going to start using our, well, first we'll define our Q out. And remember, that is A dH times 2 times G times H to the 1/2 power. That'll make importing our differential equations a bit easier. So dH dt, let's look back at our whiteboard. So dH dt is equal to Qn minus, this is Q out over AC. So this is going to be Qn minus Q out over AC. And now we can go ahead and import dC dt. So take a look at that. So this is going to be, well, let's start inside here. So QnCn, Qn times Cn minus what looks to be the concentration of the tank times the outflow. So C times Q out all over AC. So all over AC. And we are going to put that in parentheses, have an outer parentheses. We're going to minus concentration times dH dt. And this whole thing is going to be multiplied by 1 over H. Okay. And we want to return dH dt and dC dt. And that should do it for our differential equations. Now we use solve IVP to go ahead and simulate the rest of this tank. So now we're going to call up our old friend solve IVP. So res equals solve IVP. We're going to be solving dv dt. Let's define our time. So t, and just going to set that for 2000 for right now. And we'll set our t plot values now. Just going to np.linspace from 0, 0 to time end. And so we're going to go from 0 to the end time here. So t end. And our our y initials here, we're going to use a couple values here. We're going to use our initial height and the initial concentration in. We're going to set our dense output to true. And our method, we're going to be using the Rodin method. And let's go ahead, we're going to solve this. Get a nice little array here. So next step, take this into our subplots library. Go ahead, graph this out. First things first, let's get some variables assigned to this. So we're going to have, the first one is going to be our h, second one is going to be your c. So have that do that. And now we are going to have our fig dot make subplots. Fig equals make subplots. And what we're going to do here is we're actually going to change up the rows and columns because we want to see the height and the concentration side by side instead of just on one graph, so it's a little bit easier to compare. So fig.add scatter. Our x equals tplot. Our y equals, let's make this one height. We're gonna name it. Call it height. Mode is gonna equal lines. And row equals 1. Call equals 1. Let's do the same thing for our C. And this will be row 1, column 2. So let's just run that. And now we have a side-by-side comparison for the height and concentration from their initial steady state to some point in time. We can see that as time progresses, we see that our height rises and eventually stabilizes at around 6.16, 6.17 meters. And our concentration starts here at 1 meter cubed per, 1 mole per meter cubed. And it looks like we settle at around 1.25. So that's how to simulate that problem.